Welcome to Scalable Observability, a handy guide for getting started with distributed applications. I'm John Feminella. I work for a company called Pivotal. I'd be delighted to talk to you about it more, but that's not the focus of this talk. If you do have questions or comments or questions that are more of a comment than a question, I'm happy to take any and all of those. Please feel free to tweet me or Slack me or ask me afterwards. That's the RailsConf Slack. All right, so today I want to talk about the fundamental building blocks of observability as applied to applications, the kinds of applications you all probably work on, engineer, design, build, test, operate, et cetera, et cetera. And I think when people hear the word observability, that might be a confusing term or a new term to some people, or it's a term that maybe gets conflated with other things like monitoring or metrics. And I want to use this talk as an opportunity to distill some of those ideas for you and also show you how they can be applied for your own applications, whether you're running 1, 10, 100, or 1,000 different applications, whether they're all Rails, some of them Rails, some none of them for that matter. But I want to show you some tools that can help address the challenges that we'll talk about. I mean, I want to recommend a specific approach that I think will be helpful if this is a new topic for you and you're just getting started with observability in your portfolio. And then finally, I'll close with some specific advice that I think will be useful in this journey. Okay, so let's talk about those challenges that I mentioned first. I think when people look at an application that they're responsible for operating, they want to know the answers to questions like, is this healthy? Is this meeting all of the promises that it's supposed to meet? Am I processing people's concert ticket requests? Am I making widgets in the factory? Am I doing all of the things that this application or service or whatever is supposed to do? And it can be tempting to try to answer that question by measuring everything, by measuring as many things as we possibly can. And to take one maybe specific example, and let's put some numbers on it, imagine you have a system you'd like to understand the health of. So there are lots of things we could measure. And so people might start off measuring things like disk I/O or how much CPU is being used or memory. And there are lots of things we could measure for sure. And in fact, let's say that for this particular application, we record 100 different things about this application for every instance of it. So if there are 3 instances, we're recording those same 100 things for every instance of that application. So we call one of those time series that we're recording, we're going to call that a stream. And so for every instance of this application, there's 100 streams. And let's say we sample this stream at 1 sample per second, and let's say that it takes 24 bytes for each sample. That's enough for, let's say, a 64-bit timestamp, a 64-bit number, and some 64-bit identifier or metadata or something like that. So that's 2,400 bytes per second per instance of this application, and that's 240,000 bytes per second. That's about 7.5 terabytes per year for if we were running 100 instances of this application. So that seems like a lot of data. It's probably more than fits on your laptop. But if we store that in, say, S3 or some cloud service, that's not very expensive, relatively speaking. It's about $200 a year for every year of that application we want to store. So for an entire year, that's $200. So for enterprises and for larger companies, that seems like a no-brainer. Why wouldn't we want to store everything we possibly could all the time about everything? Especially if there's a problem later on, we want to be able to diagnose how that problem came about. That's a valid question to ask. Why don't we record everything? And there's often a philosophy in these places of if you can measure it and it's cheap to measure it, why wouldn't you measure everything you possibly could to understand how a system is functioning? But I think it's worth asking a question, are we measuring the right things? And when we look at the tools that were offered, if you imagine let's say we have a Java application, so not Rails, but a Java application that's using Spring Boot, out of the box, you'll see things, a whole bunch of endpoints get populated just by virtue of using Spring Boot, just by virtue of using that particular framework. And so you can pick the metrics endpoint and say, hey, I'm going to add a gauge to my application that measures the number of tickets I sold, and I want to record that and emit that in some stream. And I'm going to do that for all the events that I care about. With Ruby applications, not Rails necessarily, but Ruby applications, The runtime doesn't give you anything out of the box in terms of that. There are various instrumentation and benchmarking things you can do. And with Rails applications, you get a few different choices. You have this really low-level tooling, active support instrumentation. That's about recording events that are happening inside of the Rails framework and as they interact with your application. You have agent-based tooling, things like New Relic or other things that you have to add as a gem or a binary to the environment where your application is running. And then you have rack middleware, which is libraries that are inserted into the rack middleware stack for your application. Those are the three biggest buckets, I would say. And so now is another question of, well, what do we use to measure those things? So even if we agree about what we could measure, how do we go about measuring that? What tools should we use to do that? And there's another problem, which is we are often faced with measuring the same things for applications that are not really the same as each other. So just as one data point, across the companies that I'm working with, or that I have been working with over the past year or so, most of which are Fortune 500 companies, of this sample size I'm going to talk about, that's 1,326 applications, about 10% of those were Rails apps, so about 130. 94% of them don't use custom metrics. So 94% of them essentially accept whatever the tooling measures for their application out of the box. And 92% of them haven't changed the metrics defaults for setting up a new app. So they'll get their configuration file generated for, say, New Relic or whatever, and then they'll add that to their application and commit that to source control, maybe make a few tweaks now and then, but not really changing anything substantive about what's actually being measured. So that's a problem because if there's very little variation in what we measure for different apps, but there's lots of variation in the system topologies of these applications or in the system footprint and the cardinality, the number of instances that we have of each thing, and if there's lots of variation in the dependency graphs of these applications, maybe you have a monolith that depends on a whole bunch of microservices, maybe you have a huge service mesh of 50 different things all talking to each other. Those are very different relationships between those applications. And there's also lots of variation in the runtime versions we might deploy. Maybe the thing we have deployed to staging is different than the thing we have deployed to production. Maybe we have multiple versions of things running in production and we're in the middle of a blue-green deployment, for example. So does it make sense that we're measuring the same things frequently for all of these applications and accepting these defaults when these applications are really, really different from each other? Does that make sense to do? And even worse, because we're all people and we're humans with meat sack brains, we are prone to all the wonderful biases that come along with that, right? So a very frequent thing to do is to assume that correlation is, that data which is correlated to each other is representing a causal relationship, that one thing causes the other. So if you're not familiar with correlation as a mathematical idea, if you imagine graphing two different things and their relationship to each other, we would say that this has a positive correlation because these things are, as one increases, so does the other in about the same proportion. A negative correlation would be as one increases, the other decreases in the same proportion. Things that aren't correlated don't seem to follow any relationship in terms of one increasing, the other may or may not increase, or may or may not decrease. So here's a specific correlation between spelling test scores and shoe sizes. So it turns out that if you measure people's shoe sizes, this is a real data set, if you measure people's shoe sizes and you measure how well they score on a standardized spelling test where you ask them to spell 40 words of at least length 7 or more, how well do they do? How many of those 40 words do they get right? And then you ask them what their shoe size is. And it turns out people with smaller shoe sizes are worse spellers. So I'm a size 10.5, a US size 10.5, and I'm an okay speller, I would say. So how predictive is my shoe size of where I'd fall on this graph? And it turns out it's quite predictive. Your shoe size does, to a large extent, determine how good of a speller you are. So does that mean that your shoe size is causing your spelling ability or vice versa? No, because there's a missing variable here, which is also that as people get older, they learn more words and can spell better. And if you're a toddler, you have a very small shoe size, and you can't spell a lot of words. And if you're a 30-year-old person, you can spell more words than a toddler can, and presumably you have grown a few shoe sizes since the time you were a toddler. So there's a missing variable here that's not indicated or represented by the data. This is a very high correlation. This is 0.79 roughly. So that would be strongly indicative of some kind of relationship there. It's just that the relationship is not between those two variables specifically. So you can imagine all kinds of relationships that aren't necessarily causing one versus the other. So here's the per capita cheese consumption of Americans correlating with the number of people who died by becoming entangled in their bedsheet. So the more cheese Americans consume, the more people die by becoming entangled in their bedsheets. So does that mean that Americans are eating a bunch of cheese in bed and then suffocating to death because they are getting entangled in their bedsheets? No, one is not correlated with the other. It's just a coincidence that they happen to be related in that way. Another mistake we make when we're thinking about metrics and how we represent things and monitor our applications is that asking a lot of what-if questions leads to false or bad discoveries. So a common theme you might hear if you look at the general scientific literature is people asking questions about what does and doesn't make you lose weight. What would help someone, does eating some particular food or some particular magic berry give you some kind of superpowers with respect to your metabolism? And so you'll see a lot of studies where they'll give people a whole bunch of different diets and they'll say, you know, does eating peaches make you lose weight? Does drinking only milk make you lose weight? Does jumping up and down 5 times at the start of every hour make you lose weight? Well, eventually, if you run enough of these things, you're going to find something that coincidentally happens to buck the trend, but it's not because that thing is actually valuable. It's because you tested a lot of different things, and one of them turned out to be coincidentally beneficial. So that's how you wind up with things like this, where chocolate is the new superfood. You can eat as much chocolate as you want, and you'll become a super healthy person. It turns out all of those studies were later refuted when they when they tried to replicate those results. It didn't work because you can't replicate a coincidence. That's the definition of it being a coincidence. And then finally, the last kind of issue we have here is that when we are representing these really complex applications with these really complex topologies, with these really complex dependencies, we're often summarizing them in these really simple numbers. How much CPU is that application using? How much memory is that application using? And then extrapolating from that to some kind of understanding about whether the application is healthy or meeting its promises or whatever we'd like it to do. So here's a data set of 100 random points that are spread over a 0 to 100 range on the x and y axis. And here's some properties of that data set, the x and y averages and the standard deviation for x and y, and then the correlation that we talked about before. So since this is a relatively random data set, it won't surprise you to see that the correlation is close to 0. These variables are not well correlated because they're randomly generated. Now, here's a different data set with the same number of points arranged into the shape of a dinosaur. This data set has exactly the same properties as the other one did, but they look really different from each other, right? So those two things don't look anything like each other. Hopefully you can, even if you haven't seen a dinosaur before, hopefully you can tell that the thing on the left seems much more ordered and structured than the thing on the right. But yet, again, they have exactly the same properties rounded to significant digits after the decimal place. So because of that, it's very important to be able to understand the overall shape of things and not necessarily have these metrics that reduce things to a single point or a single value. And in fact, this is so important that you can perturb that data set over time such that you're only adjusting the significant digits that are past the last 2 after the decimal point, and wind up with data sets that look totally different from each other, yet have exactly the same statistics as the dinosaur and the random shape that we saw before. So what does it say about our applications when we measure things like this and expect to be able to have a clear or broad understanding of what's happening? And then can we overcome the inherent biases of our feeble, frail human meat sacks that are prone to making these kinds of assumptions? Let's talk about some tools that we can use to do that. So the first one that I want to talk about, if you aren't already familiar with the idea, is the idea of a service level objective. And this is essentially a promise that your application is making, either to its users or to some upstream or downstream service, about how your application is going to interact with the user of an upstream or downstream service, et cetera. And this is often broken into 3 smaller components or 3 separate components. So there's the SLI, which is the service level indicator, the SLO, which is the service level objective, and the SLA, which is the service level agreement. So what do those things mean? So a service level indicator is a thing that you want to be true. I want my application to be serving 100 requests per second. I want I want people to be able to complete their transaction in 10 seconds or less. I want this message queue to be able to process 20 jobs per minute, et cetera, et cetera. Those are indicators. It's a fact that you want to be true. The service level objective is how strong you want that, how strongly you want that thing to be true. So it's the strength of the promise, essentially. So if, for example, you are, let's say you want everybody's request to finish in 5 seconds or less, that's the SLI. If it's OK to do that for 99.9% of requests, then that's the SLO. That's the target for that promise, right? If you adjust the SLO, you're adjusting the strength of the promise. If you adjust the SLI, you're adjusting what you're promising. The SLA is the consequences for breaking that promise, right? So if you have a SLA with some service or with some application, then there are consequences when the promise is broken. So if you don't have an SLA, then you're making promises, but there's not necessarily any consequences for the promises going awry. As an example, if you have an ISP that you get your broadband from, they may say, hey, we promise that we'll give you 100 megabits per second downstream and 25 megabits per second upstream. That's the promise. That's what you're paying us for, and we promise to deliver that 99.9% of the time. That's the strength of the promise. But there's not usually an SLA for residential users, right? So if your internet goes out, like, well, sorry, maybe call in customer service and we'll give you a one-day refund. But it's not really any consequences for the promise getting broken there. So that's the difference between those three. Now, why that's important for your applications is I think it's crucial, as we'll see, to think about your applications and your portfolio in terms of what promises it is or is not making. So what do you care about being true about your application? And what you usually don't care about being true are things like it's using less than 90% memory. Like, you might care about that in the sense that, well, if it uses more than 90% memory, it might crash because I've seen that happen before. But that's not actually what you care about. What you care about is that it's serving patient medical records in a timely fashion, or letting people buy concert tickets, or helping people book flights, et cetera, et cetera. So that's really the shape of the thing we want to talk about with our SLOs, not these low-level details that will apply to almost any application, but rather the things that are specific to the application or service that you're thinking about monitoring. So when we think about observability, this is a little bit of a nebulous term, I think, in the industry right now. But the way I define it is that observability is our ability to understand a system given only its outputs. So if you think about like a printer, right? A printer is a very complex machine, I would say, compared to a screwdriver or a chair, right? It has a lot of moving parts, has some software and hardware, needs electricity, et cetera, et cetera. And let's say that you send a print job to the printer and lots of pages are coming out. The printer stops. It stops printing out the thing that you wanted. Well, what's wrong? How do I get it to keep doing the thing that I wanted? Well, maybe there's a screen or something that will tell me I've run out of paper and I have to load more paper. Or maybe it'll tell me that there's a jam in the system and I have to go fix it in some way. That's a very primitive kind of observability, but it gives me enough information to understand what's broken and how to fix it and what I need to do next. So that's sort of the objective we want to have for observability with our systems is, can we understand when our promises are broken, what we have to do to fix them by inspecting the outputs of this system that we've set up already. If we can only do it by doing things like attaching the Ruby debugger or bybug or something to my running Rails application and understanding why it blew up at that specific moment, that's not really going to scale very well when I add a lot more instances of that application, or when I try to service a lot more requests, or if I try to make a stronger promise, I'm going to run into trouble. And I think, crucially, the lifeblood of observability, the thing that helps us actually understand the degree to which our system is meeting its promises or not, is events. And events are really the currency of how we want to talk about observability. And there are 3 tools in your observability toolbox that you can mix and match in various ways to get an understanding of whether or not you're meeting SLOs. So with metrics, when I say metrics, I'm talking about measuring facts and sometimes statistical aggregates of those facts about the events that are happening and about the system overall. So metrics are good for things, it's almost always possible to get information by adding a metric that you didn't have before. You're almost always learning something new. Whether that new thing is useful or not it depends very much on the metric. Example, if you measure CPU and you weren't measuring CPU before, that tells you how busy the system is. But if your system's not CPU constrained, then that's not actually super useful. Most systems, especially most Rails applications, tend to be network I/O constrained. They tend to rely on some other downstream service or some database or something else that has to be fast before the application can be fast. Another advantage metrics have is that it's easy to slice and dice the way that you've collected that data to tell different stories as that suits your purposes. So if you collect, for example, information about all the tickets people are buying and how much they paid for them and so on, those are events. And you can ask questions like, how many people paid over $10 for a ticket? Maybe my ticket prices are too high if not enough people are buying that kind of thing. How many people paid $0 for a ticket? That seems problematic. Those people shouldn't have gotten a free ticket. I might have an error somewhere in my shopping cart code, that sort of thing. The tricky part with metrics is that it's hard to tell what's important prior to knowing prior to experiencing some kind of problem with your system. So people often adopt a scar tissue mentality where they'll have some kind of outage and they'll say, oh, the application crashed when we got over 95% memory. Let's make sure that never happens again. 500 PagerDuty alerts every time the application gets over 94% memory, right? So it's hard to, and if you do that for every time you have a problem, you're just going to wind up with a bunch of alerts that nobody listens to or cares about, right? So metrics in and of themselves aren't sufficiently robust to describe the overall picture of the system. We're looking at numbers, we're not looking at the dinosaur. Logging is a way of taking those, the events that you have, structuring them in a way that's easily machine readable and human readable, and also providing a stream for stuff that's not structured. Hey, I reached this point in the method, that sort of thing. So it's a stream of all of the different things you might want to record. So logging's good for a really cheap, easy way to emit information at the point that it's interesting, and it's easy to debug specific issues. Again, if you've anticipated them in advance, you can be like, oh, I know that this method is the troublesome one. I'm going to go in and add a message there that tells me about what's going on in that method. So if I see a problem again, I know how to fix it, or I know at least what the circumstances were. Again, the issue with logging is that it can lead to the sort of same kind of hoarder stuff that we talked about before. Capture everything all the time, never throw any logs away, going back 100 years, right? That might be important for some kind of enterprises or some kind of businesses. There may be legal or regulatory requirements for them to store logs. And in that case, this particular point doesn't apply. But for most applications, most of the time, it's not actually important that you store all logs forever, till the end of time. There are also lots of issues like accidentally putting something in logs that you shouldn't put in logs, or putting the wrong information in logs, and things like that. And then finally, tracing, which is, I would say, is relatively uncommon in Rails applications, is where you capture events with some kind of causal ordering. So if you have a stream of logs and you have multiple instances or multiple threads or multiple processes that are writing to that stream, then there's no guarantee that the order in which the events happen temporally is the order in which they will be recorded in the log, right? If process A and process B are both writing to the same log stream, there's stuff that's going to overlap with each other and commingle. So you won't have a sort of a transactional understanding of what happened in the system just by looking at logs. Tracing is different. Tracing allows you to attach identifiers to requests or to transactions or to whatever is of interest to your particular system, and then use that as the basis for understanding not just one event or one thing that happened, but a series of events that happened that's meaningful at the business level. For example, maybe in order to buy a concert ticket, you first have to authenticate yourself. You first have to provide credit card information. You have to do a hold on the credit card. You have to then submit the payment and get the billing information, et cetera. The combination of all those events together might be a path through the system that eventually winds up back at, oh, hey, here's your concert ticket. So you did one submit button click, but 5 different microservices did a bunch of stuff. You're going to want to understand if there are any problems there, how that bubbled up back to the original request. So it turns out there's a great, robust, standardized API called Open Tracing. And in the links for the slides, you'll be able to click on this and learn more. There's a particular implementation of open tracing for Ruby and Rails applications called OpenZipkin. And Zipkin has many different agents for many different runtimes. One of them is for Ruby on Rails applications. And because it's essentially a rack middleware, it'll work with Rails, but also Sinatra or anything else that uses rack. And so that's a really easy way to add tracing, because you just insert a rack middleware, and every request is going to get a header if it has this tracing metadata on it. So that's pretty nice. Now, unfortunately, it has limited utility for Rails applications that are essentially monoliths that don't talk to any other applications or services, because there's no request to trace at that point. You just have one thing that goes and talks to maybe a database, let's say, but then it's done. All the processing is happening in one system. Also, Rails applications tend to, as compared to maybe, let's say, Java or .NET applications, tend to have a lower branching factor. There's more of a center of gravity on maybe deploying one thing and having multiple things in your proc file, let's say, have that do the activity that your application requires. The third sort of tool in the toolbox I want to talk about are the 4 golden signals. This is a phrase that comes from Google's SRE book that was published about 10 years ago. And what the 4 golden signals are is essentially, if you're recording facts about your system and you didn't have a lot of room to choose what you could record, what should you choose? And they say that there's basically 4 things you should try, 4 things you should measure. So first is traffic. How much demand is the system facing? What is the system being asked to do? Latency is how long do requests need to wait. So if from the moment that somebody clicks submit in their browser, how long does it take before they get a response? It's important to distinguish here between the latency of requests that are successful and the latency of requests that are not successful, that fail in some way. So for example, a HTTP 500 that triggers due to the loss of a connection to a database or some other backend thing, that might get served really quickly. Hey, this is down, HTTP 500. But you don't want that HTTP 500 quick response time to contribute to the overall understanding of your system's latency. That would be bad if you counted errors as part of the system's latency, because then in order to optimize for latency, you should actually just shut down your website so that you have 0 latency, because people can't reach your site at all. Saturation is how much more can the system handle based on what it's currently doing. So saturation is really tricky because how full your system is will depend on an understanding of what resources your system consumes to process requests. So many people think, for example, their application's limited by CPUs. They really want to run on a beefy AWS machine. But actually, most of the time for most applications that are web services or websites, you're usually limited by network I/O. So the more network traffic you can send to your website, the faster you can process requests, rather than, it doesn't take a lot of CPU on the server side to render a page. So it's important to understand what's the actual limiting factor there. And then finally, from an errors perspective, we want to, the 4th golden signal is errors, which is how frequently are requests failing? What is the rate of requests that are failing, either explicitly, for example, HTTP 500, or implicitly, like you get a HTTP 200, but the wrong thing gets returned, or the stuff that was supposed to be written to the database didn't actually get written, et cetera, et cetera. So when the protocol response isn't sufficient to express any kind of failure condition, you're going to need some other way of expressing that there was a failure. You can't just look at HTTP in that sort of a case. OK, so putting that all together from an observability perspective, how we should use each of these tools, I think, in the approach I'm going to describe, is in 3 different ways. Metrics are for measuring the real work that's done by your system and trends that occur over time. Traces are for understanding specific causes of problems across services when you cross some kind of boundary. And logs are for helping humans understand what's going on and to provide a structured machine-readable event stream. So here's the approach that I'd recommend for folks who are getting started with observability. Like we saw before, there's all kinds of different topologies that you could encounter in some distributed system. And it doesn't really matter if these are Kubernetes pods or different instances of your application on Heroku, but whatever the topology is, we tend to get it represented on some really nice dashboard that abstracts away the fact that these things are really messy and are connected to each other in strange ways and so on. So that's not really that pleasing facade is not what a distributed system really looks like. And this is too reductionist a view. This is going back to this is missing the dinosaur again. So these two things don't look like each other, so we can't use the same approach to measure them. And I think the way to get around that is to embrace the inherent complexity, the fact that these systems are different, right? We don't write the same unit test for every application. Why would we, we certainly don't write the same integration test for every application. Why would we write the same or rely on the same metrics for every application? So I think there's a degree to which developers need to embrace the inherent complexity of whatever their application is and measure that accordingly. So here's what I mean by that. Let's say we have a system, we don't know anything about what's inside. What should we measure to try to understand if the system is meeting its SLOs? It doesn't matter whether the system is simple inside or complex inside or somewhere in between. What matters is, what are the questions we want to ask to understand how this system is doing? What do we want to know about the system? What's our window into the printer? How should we come up with that for each and every application that's in our portfolio? So if we could ask any questions we wanted, what should we measure? What would tell us the most about whether this system is healthy and meeting its SLOs? And I think in order to do that, we have to consider a different kind of metric. And this metric has 4 parts, 4 different fragments to it. The first part is demand, and this is similar to the golden signal idea, but it's a little bit different. And for demand, I mean, how much work is the system being asked to do? So work here is going to be a notion that's specific to that system. So if it processes concert tickets, it's probably requests for concert tickets. If it's doing video encoding, it's probably the bits per second it can emit, it's being asked to encode, and so on. So that notion of work will be very specific to whatever application, whatever microservice, whatever thing is doing the work. Second is, how much of that demand is being satisfied? If this is a system that's processing concert tickets, and we're being asked to sell 10 concert tickets a second, are we selling 10 concert tickets a second? Is that what's happening? How much of that demand is being satisfied? Third is the efficiency with which we're producing the output. So how well does that system use its resources, memory, CPU, all those low-level things, to produce output? So you can view the system as a machine that consumes memory, CPU, disk I/O, et cetera, and takes requests for, in this case, concert tickets, and turns that into concert tickets that it's selling you. So how well is the system making that work? And then finally, capacity. Does the system have enough resources to do the work that's being demanded of it? So if we measure all 4 of these things, we'll have a very specific understanding of a system that's based on the work it's doing. Now, the cost here is that we have to understand the system, right? We have to understand something about that specific application. I can't take this and do the same thing for 10,000 applications in a portfolio. But I think that's OK, because again, I think of these as tests, essentially, that the system has to meet. You wouldn't say it was correct if the system was HTTP 500, or was returning HTTP 500 once it was handling more than 1 concurrent request at a time. So in the same way, we wouldn't say a system was correct if it was failing half its unit tests. So these are, in essence, I think, another kind of test that the system has to meet. Now, that does mean you'll have to invest the effort into figuring out for a whole portfolio what's different or special about each system. What's that system doing that are its SLOs? And in many cases, that will be a new idea for some teams or some organizations. So let's look at a few examples of how this might work. So let's say you have, in this case, this is a real example of a database inside a Kubernetes cluster that has about 1,200 pods in it. The SLO around this database is the number of queries it's asked to process, and the output is how many queries it actually processes. In this case, there's a concert ticketing website that gets about 10,000 requests per minute for concert tickets. The demand is how many I'd like you to reserve my tickets, and the output is tickets that get sold without negative UX in 90 seconds or less. If you're running a patient medical records EMR system, the demand is for patient medical requests, for records requests, and then the output is how many of those records are you returning in a timely fashion. Now, what can be tempting is to set thresholds on these things. So you might say, OK, well, I want to make sure that I'm always servicing a certain level of concert tickets or patient medical requests. So I'm going to set a threshold alert here. I'm going to set my PagerDuty alert that says, hey, if I'm not processing at least 10,000 records per minute, that's a problem. But then you're getting into this guessing game of trying to figure out exactly where the threshold goes and exactly what the right number is and exactly what to alert on. And you're being asked to predict the future about when you should alert on one of these things being a problem. And I think that's the wrong way to go about it because it's too arbitrary. It's just a guess that 90% memory or that 85% memory is the right thing or that 5,000 requests per second is the right thing. What you should care about are the SLOs. But if you do want to set a threshold on something, I think you should set a threshold on percentiles rather than on specific values. Here's what I mean by that. Imagine that you record the latency of a system over time. You just take the time index for every single request that happens and the latency that occurs. So you can see we've got a relatively narrow band in which these requests are being serviced, but then we have a few outliers towards the top and the bottom. So what I think would be helpful is to order all of these requests, not by the time index, but by their value. And now we can see a kind of a different picture of a system. Most of our requests fit in this linear band that's not very tall. But then as we get towards the top or bottom ends of this band, we're seeing a really kind of a kink, a change in the slope of this curve. And if we zoom in a little bit more to one end of this curve, you can see that this occurs right about the 99th percentile. So if you were going to set an alert, this is clearly some different regime or some different kind of behavior that the system is occupying. That's where I'd set that alert, not on an arbitrary number like 100, using more than 100 megs of RAM or whatever. So using that story to understand the raw data is how we're going to get the observability for this system. So let's try a couple of scenarios to test to see how this idea works. So let's say that in one scenario we have a load spike. So the number of queries that we receive on our application goes up by 20%. The efficiency stays the same, and the number of queries we process also goes up by 20%, as does the resources we're using. So queries went up by 20%. The queries we're processing went up by 20%, and the amount of resources we're using went up by 20%. Raise your hand if this is a problematic situation, if you think this is something you would send an alert about. Raise your hand if you wouldn't send an alert about this. All right, so I wouldn't send an alert about this because our requests went up by 20%, and so did the amount of work we're doing. That's good. And we didn't change our efficiency, so that's also good. So this is the totally normal behavior of the system. Let's say scenario 2, the amount of resources we're using goes up. So here, the amount of queries we receive goes up by 20%. The output goes up by 20%. And now we're using 60% more resources. So efficiency went down. Raise your hand if this is something to alert about. Raise your hand if you wouldn't alert about this. Right, so it'll depend a lot on whether or not 60% is going to bring you too close to the capacity of the system for your SLOs. If your SLO is 50% higher than this number, and you're already at 95% at the capacity, you've got a big problem. Like that's worth alerting on. But if your SLO is 50% higher and you're using 10% of your total capacity, no big deal. Scenario 3, let's say the demand is going up over time. So let's say the amount of queries we receive goes up by 80%. The efficiency stays the same. This goes up by 20%, and the usage goes up by 20%. So raise your hand if this is something you would alert on. Raise your hand if you wouldn't alert on this. So I would alert on this because the queries went up by 80%, but the output only went up by 20%. So we're dropping a bunch of these things on the floor, or we're not meeting our SLO in some way. So it's not that other metrics aren't important. It's not that things like memory, disk I/O, and CPU are not important. But it's important to optimize for the people who will be trying to solve the problems and understand the state of the system. Who's looking at the window on the printer to understand what they need to do next? So if I could leave you with just some advice in the form of anecdotal evidence from 3 Fortune 100 firms out of that data set that I talked about before that have applied this strategy to not just their Rails application portfolio, but to the broader swath of their portfolio. They saw a mean 98% reduction in false positive rates for applications that are using that strategy. They saw a mean 1,500% improvement in correlated outcomes, meaning that when they get a PagerDuty alert, it's actually about something important. It's actually about an SLO being violated, not, whoops, Alice or Bob set an alert on that thing. It doesn't really matter, and now everyone's getting paged about it. And then all 3 of them, maybe most tellingly, have expanded this approach to new systems, not just the existing ones, and they're investing to apply this to legacy and previous systems. So I think that's a really powerful statement of how this can make a difference in terms of real-world systems, real-world companies. So if I could leave you with 3 takeaways. First, it's that observability is not a silver bullet. It's going to require a tool set. You can't magically install some library and get observability. There's no gem install observability. Now, of course, someone's going to make a gem called observability and ruin this joke. But there isn't as of the moment of this talk, there isn't one. And it requires a tool set. It doesn't require just picking the right numbers or guessing the right values. It requires a holistic understanding of a system. You have to orient what you capture around the promises you make, around the SLOs that your system is responsible for. If you don't make promises to anybody, then what's the point of your system? What is it doing, right? It's not, either it's just a hello world application that has no real substantive business value, or you don't understand what your system's actually doing. Both of those are bad places to be in if you're a business. And it's really hard to get this right. It's not that you're going to guess right about not only the SLOs or not only the way to measure them, but it's important to have a starting point. And I think the approach I described before is the place to start. So iterate on that, and you'll get to, I think, a happier place in terms of the outcomes you want. Thanks very much, and enjoy lunch at RailsConf.